Alright, so we did linear, so now we're going to do exponential. So again, I'm going to briefly go over the two different cases, and so that you can recognize the difference between the two. Alright, so comparing linear versus exponential, and we're going to spend our time in this section in exponential. Alright, so suppose that I had a balance in my account of 10,000. Alright, the balance in my account increases by 2,000 every year, and so this is a linear case, because it's the same amount each time period, each year. So every year we add $2,000. So in year one, or after year one, our balance would be 12,000. The second year, we'd add another 2, so it'd be 14,000. Another year goes by, so year 3, it'd be 16,000. And so this is a linear case. The rate of growth, the slope, would be 2,000 every year, and the initial value, B, would be the 10,000 in there. And so it'd be the line, y equals 2,000 times time plus 10,000, where time is the time in years. Every year I get to add 2,000. I started out with 10,000. Alright, so this would be a linear case. What we're going to get into in this section is exponential cases, exponential growth and exponential decline. So suppose that I have the same starting value, right? So my initial value is still 10,000. But this time, my account's going to grow by 20% each year. So the 20% each year means every year I get to add 20% of the previous years. And so that's what makes it exponential growth. It's growing at a rate proportional to its size. Each year, you add 20% of the previous year's, or that year's, balance. Alright, so when you start, you had 10,000. So then by year 1, when year 1 goes by, you get to add 20% of 10,000. So that'd be 0.2 times 10,000, which means you get to add, that's what $200 is. And so by the end of year 1, you do have 12,000. So that's the same as before, but this is where it changes. Year 2, you add 20% of this balance. So it's 20% not of the original value, too many zeros there, but of the 12,000, right? And so it's a little bit more in the second year. It's now 2,400 is what we get to add. And so the new balance after year 2 would be 14,400, so it's a little bit more. Year 3, we add 20% of the 14,400, which means we get to add a little bit more this year. It's 2,888. So you'll notice every year we got to go up a little bit more. Right? The first year we added 2,000. The second year we added 2,400. The third year we added 2,088. So it increased at a faster rate, right? My increasing rate, I increased faster. Then in the linear case was constant. Every year I added the same amount. In the exponential case, that's not the case. I add more, and I add more each year. So a little bit more, a little bit more, a little bit more. So it's an increasing rate of change. That would be exponential growth. Alright, so to formalize that, exponential growth. And we are going to eventually get into decay, but right now we start with our exponential growth. So an exponential growth is a quantity that grows exponentially when it increases by a constant percentage over a given period of time. Another way to say that is it's increasing at a rate proportional to its size. So the percent of its size every time period. So it changes, it grows faster. So suppose R is that percent growth per period, so whatever we're growing by, that's the percentage at which we're growing, like the 20% in the first example. Again, when we always deal with it, we always put it as a decimal when it goes into the equation. And so what it is we take the base equation and add 1 to it. And the reason we're adding 1 to it is because we're adding our initial value. That's where the plus 1 comes from. Alright, so the future value, so the quantity in the future, the balance in the future, is the initial value times 1 plus our percentage, as a decimal, raised to time. Time is the number of periods, right? So 1 year, 2 year, 3 year, 4 year, right? Or it could be months, it could be days, it could be hours, right? So again, units of time must match whatever we're growing by as a percent must match t. So if we're going by days, r should be the percent growth by days. If we're going by hours, r should be the percent growth by hour. So those should always match up. And so again, just so you know, and this is the equation. The q is my future value. Q naught is my initial value. And again, that's just the way mathematics and science do initial values. And t is our time, and r is our percent growth as a decimal. The picture would be at time 0, we'd start at our initial value, so there's q naught, and then we'd grow it. Grows slowly at first, and then all of a sudden it takes off. And so it's no longer a line. It starts slow, but then after a small period of time, and then it starts to shoot up really fast. And again, the faster the shoot up would be, the bigger the percentage. So if you have a big rate of growth, that grows fast. If you have a small rate of growth, that grows slower. All right, but that's the shape of the graph when you graph these. All right, so a typical example would be if we have exponential growth, again, starts slowly and then increases rapidly. Suppose this exponential equation P, all right, so P stands for the population of an island. T years after 2010 is represented by this equation. So just know the parts is important, just to recognize what the parts are. Remember, that's sort of the generic equation. Quantity in this case is a population size. So 23,000 times 1.004 raised to the t. Well, what's the initial population? At time 0, how big is my population? Which would be in 2010, which would be my time 0. Well, that's that 23 at the beginning. The initial population is estimated to be 23,000 people. The exponential growth rate as a percent. Well, the exponential growth rate comes from that middle part, right? But remember that 1.004 really is 1 plus r. So if we subtract the 1, the 0.004 is my interest rate as a decimal. If you want that as a percent, you've got to multiply by the 100 to get it as a percent. Alright, so it's growing by 0.4. I was going to say 4, but it's 0.4%. 0.4%. Alright, so it's a very small. So if this were to graph this, it would be a very, very small rate of growth, which populations don't typically grow really fast anyway over time. Alright, then the next question is, what is the population? What is the population in 2003? So remember, we don't plug 2003 in. Time is the years after 2010, which means time is 3, right? 3 years after 2010. So that's the time we're going to plug in, and it's in years. The percent is also in years, so it'd be the percentage 0.40 is my percentage. And so we take our population, 1.004 raised to the 3. And so make sure you're careful here. I always put parentheses just to make sure I'm on the safe side. And it's a very small percentage, so it shouldn't grow by a whole lot, and it doesn't. It only grows by a little under 300 people. 2, 3, 7. And again, round to the whole person. We don't want fractional people. So the population grew by about 277 people over those 3 years. So it didn't grow by a whole lot. Again, the percentage was really small, so it should make sense that it didn't grow by a whole lot. Alright, we'll stop there. We'll pick up the next examples in the next part of the video.